In this section, we shall discuss ionic bonds. Ionic bonds form when a metal atom and a non-metal atom react. Metals, usually from group 1 to 3 on the periodic table, tend to lose electrons to achieve a full outer shell. Non-metals, often from group 5 to 7, tend to gain electrons. This electron transfer results in positively and negatively charged ions that are strongly attracted to each other. Covalent bonds occur when two non-metal atoms share electrons rather than transferring them. This happens because both atoms need more electrons by overlapping to fill their outer shells and become stable. By sharing electrons, each atom effectively completes its outer shell, creating a stable structure with no ions formed. Take the example of sodium, Na, and chlorine, Cl. Sodium, a metal, has one electron in its outer shell, which it loses easily to form a stable configuration, forming a Na+ ion. Chlorine, a non-metal, has 7 electrons in its outer shell and needs one more to complete it. It gains sodium electron, forming a Cl- ion. The opposite charges between Na+ and Cl- attract strongly, forming an electrostatic force of attraction called an ionic bond and creating sodium chloride. Ionic bonding isn't limited to sodium and chlorine. To achieve octet structures, metal atoms tend to lose electrons, whereas non-metal atoms tend to gain electrons. For instance, magnesium, Mg, and oxygen, O, also form an ionic bond. Magnesium loses 2 electrons to form a Mg2+ ion, while oxygen gains 2 electrons to form an O2- ion. The electrostatic attraction between Mg2+ and O2- creates magnesium oxide, MgO. This attraction between oppositely charged ions is what makes ionic bonds strong and stable. Here are some examples of ionic bonding. Formation of magnesium fluoride, MgF2. In the top part of the slide, we see how magnesium, Mg, bonds with 2 fluorine F atoms to form magnesium fluoride, MgF2. Magnesium has 2 electrons in its outer shell, which it wants to lose to achieve a stable configuration, similar to a noble gas. Fluorine, on the other hand, has 7 electrons in its outer shell and needs 1 electron to complete the octet. Here's how the electron transfer works. Magnesium transfers 1 electron to each fluorine atom. As a result, magnesium loses 2 electrons and becomes Mg2+ ion, a positive ion. Each fluorine atom gains 1 electron and becomes an F- ion, a negative ion. The resulting compound is MgF2, where Mg2+ ion is electrostatically attracted to 2 F- ions, creating a stable ionic bond. Formation of magnesium chloride, MgCl2. Now, let's look at how magnesium bonds with chlorine atoms to form magnesium chloride, Mg MgCl2. This process is very similar to the formation of magnesium fluoride. In this case, magnesium with 2 electrons in its outer shell transfers 1 electron to each chlorine atom. Magnesium becomes Mg2+ ion after losing its 2 outer electrons, achieving a stable electron configuration. Each chlorine atom gains 1 electron, becoming a Cl- ion. So we end up with a Mg2+ ion and 2 Cl- ions in magnesium chloride. These ions are held together by strong electrostatic forces of attraction, resulting in a stable ionic compound, MgCl2. Formation of calcium chloride, CaCl2. Finally, let's examine how calcium Ca bonds with chlorine to form calcium chloride, CaCl2. Calcium has 2 electrons in its outer shell. It loses both electrons to achieve a stable electronic configuration similar to the noble gases. Here's what happens during this electron transfer. Calcium loses its 2 outer electrons, becoming a Ca2+ ion. Each chlorine atom, needing 1 electron to complete its octet, gains 1 of calcium electrons and becomes a Cl- ion. In the end, we get 1 Ca2+ ion and 2 Cl- ions. The strong attractions between the oppositely charged Ca2+ and Cl- ions forms calcium chloride, CaCl2, another example of an ionic compound.